A lot of interesting new faces in the room. Got the magic words in the title, right? Decarbonization, and everyone's thinking about what that means. And we get asked a lot of interesting questions about burning of ammonia and nitrogen-related products in flares. The purpose of the talk isn't about flaring these compounds. This is about firing these gases for energy purposes, right? For their calorific.
Firing.
So there is a little sheet going around. Please, everyone, take a second to sign in, pass it around, throw it at me at the end. And I'm going to give you a brief intro here to Bill. Bill's with John Zink Company. He is the manager of the Flare Large Replacement Applications team. He doesn't have time for all those little flares, only the large flares.
No.
11 years with Zink in the aftermarket team, mechanical engineering, Oklahoma State. Process flares course instructor. By the way, there's
Part that's wrong. I didn't get Sherry stuff mixed in there.
Oh, okay, that's a different class.
Yeah, but the part that's right, some is not right.
Oh, all right. All right. So this is the little QR code if you want to download info about the flares hands-on workshop training class that they do periodically. I forget you have a new name for it, but whatever. So Bill, take it away. It's all you.
All right, good afternoon. Now it's after lunch and after another session, we're all ready for a nap, right? I'll try not to produce sleep. Okay, I'll try. I'm not gonna promise anything. So just for a feel, I mean, we got a little bit about firing, not flaring. So there's a lot of buzzwords around hydrogen, ammonia, and what they're gonna be. That's a new, wave in the future. So how many, I know who the equipment people are. So do we have you raise your hands if you're like part of your regulatory people at a site or whatever? All right, cool. And how about actual operators of equipment, stuff like that? All right, cool. All right,
I don't have a flares backyard. I think I should, but I don't.
Depends on what, if you're boiling crawfish or barbecue, you have a flaring event on the barbecue pit sometimes on the grease. So moving right along, I mean, this is a topic, like we said, it's not flaring, it's about, burning and, this is our normal legal disclaimers or that says, of course, Coke, I mean, John Zink, we're owned by Coke, and this is the various stuff, and Sherry called us, went through this yesterday, and we're kind of, since Coke realized that, man, we got a lot of synergy between the stuff that are kind of blowing up the silos and trying to get the different product groups to work together because we're involved with heat transfer too. So somebody come ask me about well, I need more out of my burners and stuff. And I go, well, maybe you just need a better feed breeding system or something like that. If a person, selling your burners and it would save you OpEx all along anyway, you're more efficient. So there's a bunch of stuff like that. But anyway, so what's driving our interest in hydrogen? We're all about greenhouse gas and the carbon footprint, stuff like that. And so, but this is nothing new. I mean, really, in various industries, people have been burning hydrogen for a while. And sometimes it's planned and sometimes it hasn't been. Like ethylene producers and stuff, they generate a lot of hydrogen, so they burn their process already. And so there's been a lot of issues, but a lot of really time experience as far as how that works. And then sometimes in refineries, depending on how their fuel system is, sometimes they they get to a hydrogen imbalance, like maybe a hydrogen consumer goes down. They're still generating a bunch of hydrogen. Then they dump all this hydrogen in the fuel, and then they start seeing where that happens. Because a lot of folks have come to the various burn people and asked me, like, what does this mean to us? And we're going to touch on some of that too as far as the process. But actually, my question back there, but sometimes you've been doing it already. You can just go back to your other situations and look at that as well. So having somebody, on textbook stuff, tell you what's going to happen with your process. And so, but anyway, so where are we getting this fuel from is going to be another thing. And we'll be comparing the fuel comparisons, which will compare natural gas, hydrogen, and ammonia. And also other system considerations like the equipment, the safety part of it, transportation, and what's the impact on emissions and the submarine. That's the two big ones right there, the hydrogen and the ammonia compounds. So future of combustion.
how to convert the combustion process to reduce or eliminate carbon emissions. Challenges, no easy substitution for combustion, so it's going to be there. We got a huge base there already, so how do we make that better? And one of the potential solutions, like we already talked about, is, green fuels, hydrogen and ammonia. And, we've been going down this path for a while, and since the, 90s and stuff, we started changing burner technology in order to get lower emissions and stuff. And what we found out when we started pushing those envelopes, that natural gas is not our friend in the burner world. It really isn't. Because the flammability ranges of the of natural gas is much narrower than the other components here. So, the burner may work in with a blend, and because really as a burner manufacturer, we love hydrogen. It reacts so fast to combustion. And so it makes the burner real stable. But when we got a year from that blend, and we go ahead and have natural gas, the burner may become unstable, which it has some issues. And along those lines, that's really took the industry about 12 years to understand as we progress burner technology to ultra low NOx burners. Really the ultra low NOx burner technology, no matter whose technology it was, let's call that was the square peg, and the heater was the round hole. And we're trying to make that fit. It took us 12 years in industry through the API to make the round hole squared, which I'm talking about the heater. Within API 5.6, we finally went through studies with that and funding that and made that correction. But now we fully understand the ultra low NOx burner technology in order to how it fits in the furnace. That doesn't mean to say that retrofits are still not problematic, but now we have defined guidelines to help keep us safe. Because otherwise, within those 12 years, we've had a lot of flame issues and stuff. And the burner get a bad rep, really was being asked to do something he really wasn't ready to do. And the reason why I'm saying that, I see the similar thing, we're going to build these alternative fuels again. Hydrogen. Hydrogen, like I said, we love hydrogen. But it also generates a lot of NOx. Talk a little bit about that as well. Also, people are talking about transportation. So they go ahead and liquefy it. European communities thinking about all they're getting geared up for liquid hydrogen deliveries. And a lot of people say, well, we use existing infrastructure such as LNG tankers maybe to bring it over there. But we'll touch on a little bit on the properties here relative to the what hydrogen is and relative to LNG is the boiling point to the whole. So in order to if we're going to use an LNG tanker to transport liquid hydrogen from the Gulf Coast to Europe, LNG boil off rates typically like 0.1% per day. We use the same vessels, the same amount of insulation. The boil off rate is 1%. That's a huge volume. Takes 10 days to get there. That's 10% of the volume. Plus the fact that the heating value is much less as well than in Africa. So there's a huge imbalance around that. So there's going to be a lot of learning, is what I'm saying, as we go down these paths, much like what we had with the ultra low NOx burner technology. And well, that's all the drive and regulatory stuff and issues that go into it. And so where are we getting it from? I mean, some of the hydrogen we're getting from water electrolysis, and then the steam methane reformers and the ammonia. There's a lot of it. Actually, like 5 years ago, one of the major U.S. Ammonia producers had told me off to the side. I was at the site and they said, we're going to market ammonia as the next fuel. Now, what drugs are you on? How is it going to work? Anhydrous ammonia? Gee, we can't get anhydrous chlorine in some plants. And now you want to with tons of, but it's coming that way. It's going that way. And so, the green stuff we're talking about, wind and solar versus the zero carbon, blue for the fossil source, the methane reformers, and then we have the carbon capture. We're going a lot of stuff and in gray. Then we have other colors too. It's pink. There's all kinds of different classifications of where this hydrogen and alternative fuels are coming from. And here's some of the hydrogen infrastructure, which we kind of touched on around relative to shipping on ships, and now we have it to pipelines and stuff. I mean, we've got some infrastructure already, which is the better way to do it. We're still with gas, not liquid, so that's really good. And we see a lot of people are looking at rationale about putting in hydrogen producers at site versus having to transport it. But then they're looking at being able to export it out of the facility and carbon capture it at the site. So there's a lot of good infrastructure keeping the hydrogen as a gas, which is good. And you can see relative to where the production units are, and it's along the pipelines, and there'll be more of that to come. And here's the ammonia production. This only went to 2014. It's even higher now and continues to grow. Here's some about fuel properties. The hydrogen is a very small molecule. At one site they refer to it as being slippery because it leaks out. It's so small it leaks everywhere. And so that's a consideration relative to the pipe and transmission. And ammonia is roughly equivalent to natural gas as far as mole weight and size. So that's not much of a problem as leaking as opposed to hydrogen. And of course, the heating values are differences in the flame speed. Hydrogen is 7 times faster than natural gas, and ammonia is slower than natural gas. Why is that a problem? Well, the reaction time for the hydrogen is much faster, and that's why it generates such NOx. The ammonia generates a bunch of NOx as well. That's because it's in the fuel balance versus the flame temperature. And of course, they're all initial temperatures. But then, like I said, you look at the molar weight on that first line between the natural gas, the hydrogen, and the ammonia. You see the big difference there. And then the heating per discussed, you see natural gas 977 there. Natural gas varies across the country. Some places it's 920, it's 980. See what the ammonia is. That's definitely pretty good there in the 300s, and 425, and the hydrogen in the 300s. And the flame temperatures, you see the hydrogen is much higher. And the flame speeds, like a huge order of magnitude difference. This is centimeters per second. The natural gas relatively low there, really fast hydrogen, and this is really slow. Then the flammability range, like I mentioned earlier, natural gas, as when we started changing burn technology, this became more of an issue. See the flammability range of hydrogen, huge range. It burns almost anywhere. It oxidizes fantastic. We love that stuff. And then ammonia, that's got a decent one too. It's better than natural gas. Yes.
Explain the flame speed a little bit.
The flame speed.
Yeah, what is it?
The flame speed is relative to the flame. Think of it like a flame. Do you have a barbecue grill? You ever barbecue? Right, and you turn off the fuel, you may hear it pop back somewhere. Sometimes it pops inside there. That's because the flame speed is faster than the velocity of the gas jet. So that flame now comes back inside that little materials. And the technology on most gas burners is like a premix. So the flame is faster than the jet velocity. So the jet velocity of the natural gas or the fuel, and the flame front where it burns. So in case of hydrogen or a lower velocity gas stream, the hydrogen will burn a lot faster back here. So let's say you have 10 feet per second, the gas jet. The hydrogen burns back here. The natural gas would be burned right here. The ammonia would be way out here, longer flame. Does that answer your question? And like I said, the burn people love hydrogen because, and flame people love hydrogen because there's no big long flame. It is down, it reacts so fast, it's down low. And part of that too is that as we're learning, because that hydrogen is relatively small by lot and leaks, there's a recent paper that came out from Princeton University relative to the study of the effect of hydrogen leaks and some OH radicals in the atmosphere that are a major component for methane destruction in gas. They carry greenhouse gas. But because of this hydrogen that reacts so fast, it will take care of, it will lead that reaction first. So there's a fixed amount of OH radical in the atmosphere. As the hydrogen leaks more in the atmosphere, the reaction is going to be preferentially faster to react with the hydrogen and not with the methane. So the methane greenhouse gas effect will get worse in the short term if there's a predominant shift in more hydrogen leaks. And so that's just, that just came out earlier this year. So, like I said, there's a lot more learnings going on relative to hydrogen, alternative fuel stuff. Interest in the ammonia and hydrogen fuels. Ammonia is definitely easily liquefied, easy to transport for sure, definitely. Doesn't have the boiling point, does not leak as easily. Consumes cost per unit, really, cheaper than the hydrogen for sure. And it does reduce the combustion air fan side because its air requirements a little less than, this is all reference to the natural gas. The hydrogen, there's a big emphasis that, continued development of hydrogen hubs and infrastructure, high amounts of flue gas recirculation and aggressive staging of the fuel as a part of the technology we use at burner to reduce the NOx. And there's going to be even more going on with that. I mean, several of the burner manufacturers are investing in having, in-house ammonia facilities at their plants in order to help, bring that technology more with more R&D inside their R&D centers. And it's definitely not as hazardous as ammonia. And reduced combustion air and induced draft size, because since hydrogen does react so quickly and requires less oxygen or air, so the mass flow in the furnace drops a whole lot. So you see a shift inside the heat flux inside the furnace relative to natural gas firing stuff. So there's a lot of other things to consider there relative to the effects it has in the process heaters when you swap out the fuel components, especially the hydrogen. And so here we have the combustion fundamentals relative to combustion air and fuel gas impacts. There's 22% less air requirement for hydrogen, 13 less than ammonia. Again, this is reflecting to natural gas. And should have really probably had different colors for the three, that because the blue is the fuel, that kind of orange is the air, and the gray is the products of combustion that's generated off the particular fuel. And you can see with the natural gas being the standard, the ammonia, the next one, requires more fuel for a given heat release you want. If you want to heat up something to say 1 million BTUs, it's for argument, it's going to take you more ammonia than natural gas to get that desired heat. And the combustion products in the air will be less, but the combustion products will be higher. Hydrogen, you see, is going to require a lot more hydrogen because the heating value of the hydrogen is so much less than the natural gas. Almost, natural gas is over in the 900s, hydrogen's in the 300s. So you see, it's going to be taking more. So the system pressure, you need to squeeze more pressure in the system. But you see the air requirement is much less. It's this way here. You see the trend here. And the combustion byproducts is less. And that's because it's less air. And I say air because air is oxygen and nitrogen. That freebie of nitrogen in the air, 79, 80%, that freeloader goes in there, right? So if you have less air, that's less total mass. And also, at BOP that was mentioned earlier is the balance of plant piping considerations. You have to consider now the ASME and NFPA codes relative to boilers. That's where the NFPA part comes into, more so than in process heaters. And then the ASC pressures and stuff, because the existing systems will have higher velocities and higher pressures when you're using hydrogen with the higher pressure drop. And also, because of that hydrogen is likely to leak, not just externally, but also through valve. So your valve specification will have to change. I've seen it at a plant because it, besides being with, the jobs prior to that, I was with ExxonMobil and, for a number of years, and, we would have an isolation valve around a hydrogen compressor. It would leak through all the time. And so we would take that valve out, test it, and it would pass leak test, and they had certain criteria. Then we went ahead and put it into a different application. It didn't do anything to it. It didn't leak at all. Because the hydrogen it just found its way through it because it was such a small molecule. And the pressure were different too, really, actuality. Ammonia is, as we know, a big hazard. Definitely more hazardous to personnel, more toxic to personnel and the environment to exposure versus the other two fuels. But it also has, because of that heavy base, it's also a high concentration of corrosion products can start be generating as well. Because, we're talking about most of it could be anhydrous ammonia, and you have to deal with that stuff. So that's be a lot of other corrosion process that happens. When that ammonia producer was telling me about their want to go to fuel with that, after I, got it off the floor and asked them, I said, so which market do you really think we're going to do this? Oh, in marine business. I said, oh, so that works out good. Yeah, so you have this big anhydrous ammonia tank on a ship in the middle of the ocean. I said, but one thing good about it is that you have plenty of water to mitigate that thing if it leaks. You can flood the whole damn thing. So you have plenty of water to knock it down. But I wouldn't want to be the guy that ship. And again, burner impacts, the flame speed concerns between which are ones, flame detections, because that's get it to a deal too when burning high hydrogen fuels. Not only is the flame speed different, but the spectrum, visible spectrum is also different. So some scanners may be a little bit more challenged around picking up in the conventional scanners that are used for flame detection. And burn technology concerns, depending if it's what we refer to as a raw gas or a pre-mixed one, because those burners that are pre-mixed, it does very much like what your barbecue pit does. It will burn back in there with higher percentage of hydrogen. And then boiler impacts, equipment's convection section pass modifications. That's because of the less mass flow of the flue gas combustion products. The heat balance in the boiler will definitely be affected more so than process heaters. And the big time NOx reduction methods are likely needed for that. And then also the thermal analysis of the difference between the heat flux profiles of burning the alternative fuels. The emissions, burner NOx results, greater thermal NOx in hydrogen versus the natural gas, a lot hotter flame temperature. For those who don't know, in ultra low NOx burner technology, what we all do there is try to reduce the flame temperature. We're not reducing heat level. We just do it by using that preloaded nitrogen to go in there to help absorb the combustion reaction. That's all it is, a reaction. Heat of that reaction, which lowers the flame temperature, which then attacks the thermal NOx. So there's three different ways for NOx to be generated. One's thermal NOx, one's fuel NOx. That one's prompt NOx. That's another animal altogether there. But there's no prompt NOx contribution from the hydrogen. And of course, the influence of the hydrogen on the NOx emission strongly depends on the burn technology, which it does. Mitigation, add or increase the FGR, which is flue gas recirculation. That's where we try to reduce the flame temperature even further. But you get to a point where you may start getting into more burn stability if you start reducing it so much. If you start shifting, because it's chemical reaction, right? So if it starts the reaction temperature starts to drop off, the flame may not be as stable. And then, of course, more aggressive fuel staging or remote fuel staging. Again, this is another technique. Instead of bringing in the external flue gas circulation to the burner right there, we go ahead and inject the fuel out into more of the inert part of the furnace or the boiler in order to reduce the flame temperature or lower the heat flux inside the furnace. So now we're talking about ammonia emissions. Oh, yeah, it's a precursor for NOx because it's got fuel bound, nitrogen in it. That's part of NOx. It's a big nitrogen thing, on the, for the other side, it's, the NOx in the air. Here we get NOx in the fuel. Definitely we don't like that. As burner people, we don't like that. So, and there is, the flame temperature is higher of the ammonia versus the natural gas. So it also shifts more on the thermal NOx part. So, there's different technology we use there. We go to like a reducing atmosphere or fuel rich condition of burn. We try to control that. So we're all just tweaking the reaction in order to try and reduce that thermal NOx, the challenge before us. And like I said before, it took us 12 years to figure out how, staging fuel took care of, and the effects on process heaters and stuff. We have a learning curve here as well. And typically it's like several hundred ppms with an optimized burner for the ammonia and several thousand ppms. I mean, typically with stage fuel, ultra low NOx burners, since we're talking ppm, we're talking, current technology that's been out there for a while, like maybe 20 ppm thereabouts. So various burn technology coming out are getting, sub 10 ppm or sub, even 5 ppm now. You see on, ammonia, it's from several hundred to several thousand. So then we go, okay, we have to do a post-combustion treatment now. Consider how to take care of the NOx of that. Now we're all taking care of the carbon element. We won't have CO2 coming out there, but we have this, bucket load of NOx we got to shovel out. So it's going to be the post combustion treatment with SCRs, which I don't use sell them too. I don't. It's just an operating expense all the time. It just increases a lot of expense operating plants. So R&D is continuing. Everyone's doing R&D on that. Hydrogen test burns at Tulsa, we've been doing, even before 21, because like I said, a lot of plants were already doing it already, and we were reacting to that even back then prior to it. So ultra low NOx burner technology, fresh air, preheated air, that comes into it when you deal with thermal NOx. And some burn technologies, even the latest stuff that's out there now, this preheated air does not impact it as much because of technology employed there. Additional flue gas recirculation for NOx reduction is pretty significant, which we're seeing in the newer burner technology. So we get down to the single-digit NOx emissions, and this is like for the hydrogen part of it, and it's very stable for the high flue gas recirculation rates. You see the blue is the hydrogen fuel. This right here is a NOx on ppm range, and this is percent of flue gas recirculation. See, with hydrogen, you can go way out on the amount of flue gas recirculation, which is the index to reduce, the flame temperature. Natural gas, we are pretty much limited there on how much we can get flue gas recirculation here. Of course, we don't need as much because the flame temperature is not as high. That would be probably a good thing to throw in there too, relative to the flame temperature. We're looking for the adiabatic flame temperature to reduce it. And ammonia, we're still, we're testing that now. We've, and as other people are, creating facilities to handle the ammonia and the R&D parts moving forward on that. So in conclusions, I ran through this pretty quick and stuff, so I'm not going to dive deep into it, but this is all like new emerging stuff. And we're just touching on some of the things that we see as of right now. Not to say it's not a good thing, just that there's some learning to be put forward. I love the hydrogen part of it. It's got to be in its right place because there's so much more we don't understand relative to when we start expanding it out. Is special design systems, burner modifications, new larger gas trains, support the fuel of ammonia. I mean, some people are not looking at using ammonia as a fuel as much as a carrier of the hydrogen. You get transported from A to B. It's much easier to transport than liquid hydrogen. Now, which is a big deal too, and then the separation of hydrogen and nitrogen, which, you know, has a lot of value as well. It is much better to transport it that way, but then now you're dealing with all this ammonia, right? And anhydrous ammonia get from point A to point B, and it's not a silver bullet, it's not a slam dunk one way or the other, we are learning more. High NOx, of course, like we said, which we alluded to, the EHS concern, the safety concern relative to handling both ones, and then, you know, if we use the liquid hydrogen to transport it on existing infrastructure such as, you know, tanker trucks or shipping, it's a pressure problem concern too. That's why, you know, the ball price is so high, and as the pressure is going to come up, we have to do something in that transportation mode in order to handle it. Otherwise, it's going to continue to rise in there. So then what do? You get the hydrogen out at sea, or you go ahead and then have to burn it in the ship for part of the fuel, and then you have to deal with the NOx that's generated off of that. So there's a lot of arms and legs in there that we have to get developed, and we are working on a lot of those things as an industry. And then the other post-combustion treatment technologies, which tend to use ammonia again, the SCRs and SNRs, and then of course the area of active a lot of development there. So anyway, I didn't put this all together, but you know, some of my cohorts there, so that's the credit to those guys. And we did do Mark did this very similar presentation for the American Film Research Committee earlier in last fall. So, any other questions? That's fine.
What about like other pollutants like PM?
Yeah, not so much in the hydrogen. I mean, that's definitely a plus in that but in the ammonia, there'll be some more PM. Just, I mean, PM5, PM 2.5. The subplaces are getting into that, used to be PM10, 10 micron. So it's shifting. So it's that's going to be part of the issue as far as how we develop the R&D and see what the post-combustion products are going to be. Yeah, definitely right. That is a concern. Do I have the answer for it? No.
What about just hydrogen though? There be any PM expected?
No, not a problem. So
Just not.
Yeah, just the NOx, and there's ways we do that. I mean, carbon capture is going to be the biggest deal on that. That's the first tool out the box to take care of that in carbon. Well, because we're going to drag the NOx. I mean, either through SCR, there's another way that we take care of the NOx. And some technologies can have that are being developed in that low NOx range, that, you know, so single digits can handle it to 80% hydrogen. Not quite 100% yet, but we're still having R&D move that. So we're getting closer, you know, 80, a little bit higher than 80% hydrogen. We're getting close to having, you know, single digit NOx numbers. Much sure that what it is now, even with current technology of stage field NOx, it's much higher. You know, it could be up to 50 PCM. And so, you know, like the R&D is still moving that way, that we get 80% now, sub the single digit NOx. Any other questions?
Great, thank you, Bill.